Thank you for attending RheoSense's webinar, Fundamentals of Viscosity, Newtonian and Non-Newtonian. RheoSense is the leading viscometer manufacturer headquartered in the Bay Area of California. Our core technology, VROC, also known as viscometer, rheometer on a chip, has been redefining the viscometry industry. We have a wide customer base, including many Fortune 500 companies. We mainly work with customers in industries such as biopharma, oil and lubrication, or inks. My name is Grace, and I am in marketing. Today, I have my colleague Ivan Akramichev, our superb application engineer, who will be presenting today. We also have joining us David Nieto, our rheologist expert, and Lulu, our technical specialist. On this slide is all of our contact information. Now, I will hand the mic to Ivan, and let's begin.
Hello everyone, my name is Ivan. Thank you Grace for the wonderful introduction. Today I'm going to be talking about the fundamentals of viscosity in terms of both Newtonian and non-Newtonian fluids. So first question we should ask before we go any further is, what is viscosity? Well, viscosity in its simplest terms can be defined as a fluid's resistance to flow. If you have a low viscosity solution, such as water, it will require a low driving force to push at a certain speed. But if you have a high viscosity solution, like honey or tar, something along those lines, you will require a much higher driving force to push the sample at the same speed. Now, how do we characterize viscosity? How do we measure viscosity? Well, the easiest way to look at viscosity is by looking at a parallel plate model. Let's say you have two plates which are parallel to each other and have a gap in between them filled with your sample fluid. The top plate moves at a velocity v1 and the bottom plate is static. Well, in this case, there are two parameters that will be key for us to determine viscosity. The first parameter is the shear stress, and the second parameter is the shear rate. To measure the shear stress, we take the force required to move the top plate and divide it by the wetted area of the top plate. To measure the shear rate, we take the velocity of the top plate and divide it by the gap depth. Now, the viscosity is just the ratio of the two. Viscosity is the shear stress divided by the shear rate. The shear rate calculation is different depending on the actual geometry used. In this case, it's very simple, but it can get a little bit more complex when you're dealing with different geometries. It is only well defined for a few such geometries, such as parallel plate, cone plate, circular slit, and rectangular slit. At RheoSense measure viscosity. Well, our technology is called VROC, which stands for viscometer rheometer on a chip. And in essence, this is a MEMS device with several pressure sensors built into it and a small glass flow channel bonded on top. Now, before I get into the specifics of how this works, I'll talk a little bit about the advantages. The advantages of such a design are that it offers a very wide dynamic and shear rate range with small sample volumes down to 50 microliters. It allows for very fast measurements with high repeatability. Now, how does this happen? Well, the way our system works is by having several pressure sensors lined up inside a rectangular flow channel. What happens is, as your fluid passes through this flow channel, it experiences a pressure drop. This pressure drop is described by the Hagen-Poiseuille equation. We use this equation to convert the pressure drop that the fluid experiences into shear stress. Now, the shear stress is proportional to the pressure drop times a constant that's dependent on the flow channel dimensions. Meanwhile, the shear rate is dependent on the flow rate times another constant that is dependent on flow channel dimensions. We control the flow rate by using a syringe pump, and we measure the pressure drop, and we control the flow channel dimensions, allowing us to control shear rate, measure shear stress, and therefore measure viscosity. We have several instruments that make use of this technology, the primary ones being the MVROC and microvisc units. The MVROC is a lab-based viscometer that allows for a very wide shear rate and viscosity range with very small sample volumes of 50 microliters or less. It also comes with optional temperature control. The microvisc, on the other hand, is a unit that trades some of the range and shear rate and viscosity range flexibility in exchange for portability and ease of use. The microvisc is portable, battery-powered viscometer that can be taken with you anywhere. Beyond these two instruments, we have a couple of others, primarily the EVROC, which is our extensional viscometer, and the HTS VROC, which is our high temperature, high shear version of the MVROC. Now, how do we define a Newtonian fluid? Well, fluids are considered Newtonian if their viscosity is independent of shear rate. That is to say, if you can look at this graph on the left, you can see that as our shear rate increases, our viscosity stays the same. And in fact, when we plot a best fit line, we see simply that our viscosity is equal to 1.93. Another way of looking at Newtonian fluids, in a Newtonian fluid, the shear stress and the shear rate in your test will be linearly proportional. So if we plot a best fit line here, we see that the shear stress is equal to the shear rate raised to the first power times a constant that is, in fact, our viscosity. Very simple. This makes Newtonian fluids very easy to characterize, as you only need a single viscosity measurement at any shear rate, and you will immediately know everything there is to know about your fluid. What makes a fluid Newtonian, and what are some common types of Newtonian fluids? Well, common Newtonian fluids are water, mineral oils, low concentration proteins, benzene, and then there's many solvents like ethanol, isopropanol, MEK, all Newtonian fluids. Typically, these are fluids that have molecules which are small with low molecular weight, or if they do have larger molecules, these are rigid sphere-like molecules that do not exhibit significant anisotropy, such as in the case of the low concentration proteins. That is to say, they do not have, they're not significantly longer than they are wide. They're roughly round. What is a non-Newtonian fluid? Well, a fluid is considered non-Newtonian if its viscosity is not independent of the shear rate. As an example, one type of non-Newtonian fluid is a pseudoplastic or shear thinning fluid. In that case, the viscosity is inversely dependent on shear rate. And as you can see in this graph here, the higher our shear rate goes, the lower our viscosity gets. Shear thinning fluids are very common among non-Newtonians. Another type of non-Newtonian fluid is dilatant or shear thickening. This type of fluid has a viscosity that actually increases with respect to shear rate, such as in the graph on the left. Several other types of non-Newtonian fluids. We can also have thixotropic fluids, where fluids exhibit time-dependent behavior. That is to say, once you start shearing the fluid, the viscosity will change over time, and when you stop shearing the fluid, the viscosity will continue to change for some time. You can have Bingham plastic fluids, which are kind of an ideal fluid. These are fluids that exhibit flow only above a certain shear stress. You can also have Bingham pseudoplastic fluids, where the fluid exhibits flow only above a certain shear stress and is also shear thinning. In the graph on the left, we have the shear stress versus shear rate plotted for all of these non-Newtonian fluids, with the exception of thixotropic fluids. Now, a few common examples of non-Newtonian fluids. For shear thinning fluids, you can have polymer solutions, monoclonal antibody solutions at high concentration and high shear, paints. For shear thickening fluids, you can have cornstarch solution, wet sand, and silica suspension in PEG. For thixotropic fluids, you can have yogurt, gels, clays, and colloids. For Bingham pseudoplastic fluids, you can have ketchup, mayonnaise, and lotion. So what are some properties of non-Newtonian fluids? Well, shear thinning fluids typically have molecules with high molecular weight and significant anisotropy, such as in the case of polymer solutions, where you have long molecular chains with high molecular weight. Shear thickening fluids are typically particle suspensions, which have large particles somewhere in the 1 to 100 micron range in moderate to high concentration. And these are particles which are non-aggregating under zero shear conditions. Thixotropic samples are generally samples with weak, reversible self-association that takes a measurable amount of time to deassociate and to reassociate. Whereas Bingham pseudoplastic samples are samples with more significant self-association, but ones where the deassociation and reassociation may be faster than in thixotropic fluids. Now, samples don't necessarily have to just fall within one of these categories. You can have samples which are both thixotropic and shear thinning. You can have samples which are pseudoplastic and thixotropic. And you can even have samples which are shear thinning and shear thickening in different parts of the shear rate range. So, how do we characterize non-Newtonian behavior? Well, a simplest method for characterization for dilatant and pseudoplastic fluids is the power law. The power law reads viscosity is equal to a constant K times the shear rate raised to the n-1 power, where n is a flow behavior index value that is specific to specific samples. For Newtonian fluids, n is equal to 1, resulting in an equation that reads viscosity is equal to K. For shear thinning fluids, n is less than 1, resulting in an inverse dependence on shear rate. And for shear thickening fluids, n is greater than 1. How do we apply this power law? Well, let's go back and use one of our earlier graphs as an example. In this case, a graph of 0.5% xanthan gum solution viscosity versus shear rate. As you can see here, this is a very clearly shear thinning sample. Now, when we apply the power law to this data, you can see a very nice correlation between the resulting equation and the set of data. And we can see that our constant K is 2177 and our constant N is 0.302. Now that we have these two constants, we can then interpolate or extrapolate viscosity behavior at varied shear rates. Now, despite its name, the power law is not really all powerful. It's simplistic, but useful, and this limits its potential for extrapolation of results. Because in reality, the behavior of non-Newtonian fluids tends to be much more complex than a simple curve such as this. Because in particular, the power law ignores things such as intermolecular interactions. In reality, you can have a sample that's Newtonian below a certain shear rate and then non-Newtonian above it. as an example, we have this data set here from a particular sample. At the low end of the shear rate range, the sample exhibits very, very faintly non-Newtonian behavior. When we plot the power law against the data, you can see what appears to be extremely faint shear thinning behavior. However, when we increase the shear rate, we begin to see much more significant, still weak, but much more noticeable shear thinning behavior in our sample. And when we increase even further, we begin to see a stronger and stronger shear thinning behavior. Now, as you can see here, each of these sets of data has a pretty good correlation with the power law fitted against it. So the R-squared value is 0.95 or greater for each of these sets of data. However, if we were to go and power law across the entire shear rate range tested, you can see that the power law clearly deviates from the data in several areas, and our R-squared value is much lower at less than 0.9. What this tells us is that the power law is not ideal to be for application across a broad range, and in fact is much better for data interpolation than extrapolation, in particular due to the complexity of non-Newtonian samples. As another example of such a fluid, here we have several monoclonal antibody solutions with the viscosity plotted versus the shear rate. Now, below 2,000 reciprocal seconds, the viscosity appears to be Newtonian with no significant shear thinning, but as the shear rate increases, several of the samples begin to exhibit significant shear thinning behavior. Now, if we were to try to use the lower shear rate range, somewhere in the 100 to 500 reciprocal second range, and we were to try and use that data and the power law to predict viscosity behavior at a 10,000 reciprocal seconds, we would get incorrect values that are much higher than what they are in reality. And in turn, if we were to measure at 5,000 to 10,000 reciprocal seconds and then predict the behavior at 100 reciprocal seconds, the power law would again give us a significant overestimation, resulting in a viscosity that is much higher than it is in reality. So why is this important? Why is it important to talk about non-Newtonian fluids and to worry about how we characterize them? Well, non-Newtonian fluids can have a wide variety of effects on both your production, your processing, and your application. There are several large effects that non-Newtonian fluids can have on production. Shear thickening fluids can stall or damage equipment when not accounted for, and shear thinning samples can lead to cavitation, improper jetting, and potentially poor mixing in your stirred batch reactors when they're not accounted for. As an example, let's say you have a fixed system, you're trying to design a fixed system for a sample. Because this will be a fixed system with a fixed shear rate, your viscosity will be proportional to the force applied, or rather the force required. And let's say this is what your viscosity versus shear rate curve looks like for your sample. This is actually a cornstarch solution sample. But let's say you don't know exactly how your sample behaves. You want to do a viscosity test, but you don't expect any unusual shear thickening or shear thinning behavior. So you just use a glass U-tube viscometer, you measure the viscosity, the shear rate in your test ends up being somewhere in the 0.1 reciprocal second range, and you end up with a viscosity value somewhere in the 20 to 50 Pascal seconds. You design your system based on this viscosity value and continue on with your day. However, your system actually uses shear rates of 2 to 3 reciprocal seconds for mixing or pumping. What happens is at that shear rate, your viscosity is 100 times greater than what you measured. This in turn means that you would need 100 times more force to actually drive your fluid at the appropriate speed, which, as you can imagine, cause many problems down the line. Non-Newtonian fluids can also have a wide range of impacts on your applications. In fact, for many non-Newtonian fluids, their behavior is key to their application. As an example, non-Newtonian fluids can have an impact on the injectability of samples, as we've discussed in our previous webinar. It can have a significant impact on lubrication, particularly in applications where the fluid will experience a wide shear rate range, such as automotive oils, spreading, such as lotions and paints, where the non-Newtonian behavior of the paints is actually key to it functioning well, jetting, such as in inkjet printers, and even something as simple as the act of drinking a fluid, such as a soda. The non-Newtonian behavior of the fluid can affect the mouthfeel of the beverage. So, we know that non-Newtonian behavior is important, and it's important to characterize this behavior. Well, how do we do that? How do we measure this non-Newtonian behavior? The first step is we need to have controlled shear or controlled stress, and we need to be able to measure the other. Not all viscometers allow for this. Typically, gravity-powered viscometers such as glass capillary or U-tube or rolling ball viscometers cannot adequately characterize non-Newtonian fluids because they do not allow for controlled shear or controlled stress. The second key aspect of measuring non-Newtonian behavior is true shear. Now, for a non-Newtonian fluid, the Hagen-Poiseuille equation no longer accurately describes the fluid flow behavior, so a particular compensation is required. As an example, on the graph on the right, you see the velocity profile of a fluid between two parallel plates for a Newtonian fluid. And as you can see in the legend, n equals 1, where n is our power law index. Now, a non-Newtonian fluid can behave quite differently from a Newtonian fluid. As you can see here, whether the sample is shear thinning or shear thickening, and the extent of the shear thickening or shear thinning, all of these play a role in how the velocity profile, and by extension the shear rate profile of the fluid looks like in your system. To compensate for this, we need a well-characterized geometry to which we can apply the Weissenberg-Rabinowitz-Mooney correction factor. This correction factor is printed below. Essentially, it looks at several shear rate versus shear stress points, and it takes the change in shear rate over the change in shear stress and uses that value in order to calculate the true shear rate. Here is an example of the Weissenberg-Rabinowitz-Mooney correction factor being applied. This is a data set of 1% Methocel solution, which is a shear thinning solution. The apparent viscosity values, the black circles, are the ones that are initially measured. The Weissenberg-Rabinowitz correction is then applied to result in the blue circles. Now, let's say that we were very interested in the viscosity behavior of this fluid at those tested shear rates. So what we would do is we would then apply the power law to interpolate the viscosity values, or the true viscosity values, at the target shear rates. Last but not least, in order to properly measure non-Newtonian behavior, we need to match our viscosity tests to our process shear rates. As we've seen, some samples can exhibit surprisingly non-Newtonian behavior within certain ranges. This means it can be difficult to understand your sample's behavior under production or application conditions without testing under those same conditions. And here you have a graph of several common applications and their shear rate ranges. We have brush and roll coating, injectability, engine oil ranges, inkjet ranges, injection molding and extrusion for plastics, screen printing, and flow coating and mixing, which covers a very broad range of topics. Now, as you can see here, some of these applications fall outside the range of a typical rheometer. However, the vast majority of this application range falls within the range of the MVROC viscometer. Another way of looking at it is by looking at the viscosity versus shear rate plot. Here we can see the range of the MVROC and the blue trapezoid, and the typical viscosity and shear rate ranges of various applications as the colored ovals. And as you can see, again, the majority of these applications fall well within the range of the MVROC instrument. Now, beyond the shear rate range, the MVROC offers several key specifications that make it an ideal instrument for non-Newtonian characterization. It offers automated Weissenberg-Rabinovich correction for true shear rate determination. It also offers low minimum sample volumes, temperature control, and a high accuracy and repeatability, which in fact make it a great tool for intrinsic viscosity measurement. Now, intrinsic viscosity can be used for molecular weight and molecular shape determination. And we will actually be discussing this in our next webinar on intrinsic viscosity. It also offers another key feature for some applications, that is the lack of air-fluid interface. Now, for some samples, an air-fluid interface can cause difficulty. It can lead to two challenges. The first is sample evaporation. For volatile samples, it can be difficult to test using a cone and plate, as it will require a very careful setting of the gap. And as your sample evaporates, you may have to worry about solute concentration changes in your sample. The second issue is more specific, but some samples can form films on the air-water interface. As an example, protein solutions can form irreversible protein networks on the interface. What happens is the proteins migrate to the interface to minimize surface energy. They partially unfold and aggregate, forming a gel-like network on the surface. And when you go to test this with a cone and plate device, what happens is instead of measuring the bulk viscosity, you're in fact measuring the viscosity of this gel-like network, which results in, as you can see on the left, results in a false shear thinning reading that can affect your results and your conclusions. Whereas in our case, we don't have any air-water interface, so we just measure the bulk viscosity behaving as it would actually behave. All right, that wraps it up for our webinar on Newtonian and non-Newtonian characterization. I'd like to thank you all for your time and hope that this webinar has been educational. We're now going to take several minutes to answer questions from the audience, and I'm going to go ahead and answer these in the order in which they were given. First question I have, for NVROC chips, are readings affected by flow rate? Well, the answer there, as long as the flow rate falls within the range available to the chip, then the readings will not be affected by the flow rate. Okay, we have another question here. Can you do temperature sweep and step rate increase using the instrument? The answer is yes, we can. The instrument is capable of both temperature sweeps and shear rate sweeps. And in fact, you can do both simultaneously. So you could generate a set of data that has both temperature and shear rate variation and the Weissenberg-Rabinowitz corrections for each of those temperatures. Another question, could I use my own final product syringe to run the test? Unfortunately, no, you cannot. The instrument requires the dimensions of the syringe to be very well characterized in order to function accurately. However, you can easily load the sample from your syringe into our syringe by just removing the plunger from our syringe and backloading the sample. Another question here. How do we do the correction? Do we need to apply it manually? The answer is no. The Weissenberg-Rabinowitz correction is built into the software. When you see non-Newtonian behavior, you simply press a button and the correction factor is automatically applied to the software, from the software. Another question. My question is, if the solution is volatile and evaporates over time, how do you accurately measure the viscosity? Well, in our case, it's quite simple. Because the VROC chip is enclosed, it's simply a glass flow channel with a MEMS device underneath, and there's no air-fluid interface other than the outlet. There's minimal evaporation going on in the sample. So you can leave the volatile solvent inside the chip, and it won't evaporate, and we'll just measure as normal. Now, for cone and plate systems, it's doable, but it's a much more of a hassle. The only real way to do it with a cone and plate would be to set up a system where the area surrounding the cone and plate is saturated with the solvent vapor, in which case you could test without having to worry as much about evaporation. Yeah. All right. Another question. Is there any limitation on fluid that can be determined with your instrument? The answer is there's a small handful of limitations. The first being the viscosity range of the instrument, of course. The second limitation being the particle size. We typically deal with flow channels that are in the 50 to 300 micron range, and our upper limit for particle size is about 50 microns. Last but not least, we can test practically any organic or inorganic solvent you can throw at the system. We can use NMP, we can use MEK, we can use THF. The vast majority of these fluids are compatible with the instrument. However, very strong concentrated acids and bases are not compatible with the instrument. And we also cannot use hydrofluoric acid due to the presence of glass inside the system. Okay, for non-Newtonian fluids, can viscosities be correlated with concentrations? The answer is yes. What you would want to do is you would want to test your non-Newtonian fluid at the same shear rates for each concentration. You would then be able to plot both the non-Newtonian behavior at each concentration as well as the concentration-dependent behavior at each shear rate. All right. Next question. Has your instrument been used in actual industry? Can you give some examples? It's a very broad range of industrial uses and applications that our instrument has been used in. Of course, the primary, the biggest industry for us is biopharma, which covers a very broad category of use cases. But we've also been used in industrial applications such as automotive oil testing, lubrication testing, ink testing, even testing things like lotions or eye drops. It's a very broad category of applications. Okay. So, next question. For non-Newtonian fluids, using a cone and plate to measure viscosities, the practice is to use the same settings across samples in order to have comparable results. What happens when the viscosity is outside the range of the shear rates used? Well, in that case, you can do one of several things. You can have an overlap between your samples of several shear rates, which means that even if one is outside the range, you can still compare it with the other ones. Or you can use the power law to interpolate your viscosity values at shear rates in order to get viscosity values at the same shear rates for your different samples. Okay. Another question. How many shear rates can we measure at one time? How long will it take? Well, the number of shear rates you can measure at a time is only limited by the amount of sample you have inside your syringe. I'd say we can typically get about 10, 15, 20 shear rates from a single syringe, depending on the particular shear rates used. How long does it take? Well, we say that our measurements take less than a minute. This is true. Typically takes significantly less than a minute. I'd say our average run time per shear rate is in the order of 10 seconds, which means that for 15 to 20 shear rates, you're looking at less than 15 to 20 minutes, most likely in the ballpark of 5 to 10 minutes. Okay, next question. Is there any requirement of the sample to be measured at high shear rate? If I want to study injectability, can we measure a sample of any viscosity at 1 million reciprocal seconds? The answer is not quite. The maximum viscosity is inversely proportional to the maximum shear rate. We can do samples of about 3 to 4 centipoise at up to 1 million reciprocal seconds, and it does the maximum viscosity does decrease from there. Okay, I have one last question here. Do you have examples of comparison between cone and plate and VROC? I do have one example here with me today. That is an example of Newtonian versus non-Newtonian fluids. As you can see here, this is a plot of xanthan gum solution. This is data that has been taken both with an Anton Par MCR rheometer and our instrument. As you can see, both instruments are in very good agreement with one another, and whereas the rheometer can attain somewhat lower shear rates, our instrument can attain much higher shear rates. All right, well, I'm afraid that's all the time we have for the webinar today. Once again, I'd like to thank you all for joining, and I hope you join us for our next webinar where we discuss intrinsic viscosity measurements and what their use is.